Now that we've developed the material and energy balance for the reactor, we can start thinking about the influence of kinetics and the fact that some kinetics present particular problems. So sometimes equilibrium limits how far we can go with the reaction, but now that we have the energy balance and the material balance, we can think of clever ways to design this reactor so that we can negotiate the plane and we can find our way to higher conversions and better reaction rates and design systems that are small and have a reasonably sized volume. So we are talking now about non-isothermal reactor design, and we are going to look at the influence of equilibrium conversion. So when talking about equilibrium, we are largely talking about the fact that the forward reaction and the reverse reaction will reach some stage where the concentration of the participating species are in some kind of balance. So that's the stage of equilibrium. There's a balance among the concentrations such that the net reaction rate is zero. So here's a simple case where we have component A being converted to component B, but the reverse reaction is also possible where component B is converted back to component A. And generally speaking, the reverse reaction is always possible. It is always possible for the reactants to recombine and give us back the reactants. And this is something that happens to different extents for different species and for different reactions. So sometimes we call a reaction irreversible, even though it's not technically irreversible, that the reverse reaction does happen. So for some reactions, it appears to be irreversible because the reverse rate might be much slower. But anyway, we're talking now about the case where there's a significant amount of reversibility, and so we want to know how to negotiate the plane in light of this. So to begin with, let's define the two reactions involved here. So as we said, the forward reaction rate is component A being consumed. So the forward reaction is proportional to the concentration of component A, as we see here. So R1 is the forward reaction, K1Ca, so this is a consumption of component A. Then reaction 2 is the reverse, so it's component B being translated back to A. So this is, of course, then proportional to the concentration of component B. So the reverse reaction rate R2 is K2 times Cb. And then we can also define for ourselves the net rate of consumption of component A. So component A is, of course, being consumed in the first reaction. So R1 increases the consumption of component A. And then R2, which actually forms component A, may be thought of as the reverse of consumption. So minus RA is R1 minus R2. Then, as mentioned, we are interested in this case of equilibrium. And so we are going to define equilibrium to be the stage at which the net rate of production of component A is zero. So in other words, these two reactions are balanced to the extent that the component A is not unbalanced being formed or being consumed. So at equilibrium, the net rate of consumption of component A is zero. And that doesn't mean the forward reaction is not happening. It doesn't mean that the reverse reaction is not happening. It's just that both reactions are happening at the state where the two rates are equal. So the two rates become equal at this equilibrium stage. And so if we can identify a state where the rate of consumption of A is perfectly balanced to zero, then that will be a special state. And now, of course, all of this might be at some specific temperature. So let's say nature has prescribed K1 and K2. So for a given temperature, there is a given rate constant in each reaction. And then, so that means we can't really identify anything special about these two values. However, we acknowledge that at the special case of Ra equals zero, there exists a special concentration CaE and CbE, and of course E for equilibrium. So at the special state of equilibrium, under these specific conditions, CaE and CbE, Ra equals zero. And we can say then if we take one of these terms across, then we can divide through by K2 and say K1 over K2 equals CBE over CAE. And we also then define capital KE to be this ratio. So we can define the so-called equilibrium constant, and that's nothing but the ratio of the kinetic rate constants there. Just note this notation here, it's a colon for defined, so it's not really established notation in maths. In computing, it's more defined, but anyway, that's my notation for defined. So if we have this definition, capital KE, we can rewrite this expression for the overall consumption rate of a bit differently. So this is just reproducing what we've done already. And then if we group out a K1, a small K1, then you've got CA here. And then you'll have CB. And then you'll have K2 over K1. So if you group out a K1, you need to write in a K2 over K1 here. And then we know K1 over K2 is KE. So we can rewrite this as CB over KE. Noting here that this CA and CB, those are back to the general values now. This applies to any concentration set in CA and CB. These are not the equilibrium values anymore. So we can take advantage of an equilibrium style constant and just use that to write our rate expression in this form. It doesn't mean that we are then stuck to that applying. There's nothing to prevent us just defining the ratio of K1 and K2 to be KE and then using that ratio in other places where this condition doesn't apply. It's just a definition. So in the example, you've got the same reaction, and this time you are given the Arrhenius expressions for K1 and K2, and we are asked to consider how the rates change with temperature. So if we say the conversion is fixed, what's the response of the reaction rate with temperature? And here it's simply plotted. In fact, you don't really need that conversion. I'm not sure why I said that. Well, I guess if you wanted to put in numbers for concentration. Anyway, so we could have just plotted the rate constants, right? So we find here rate 1, rate A, so that means R1. So that is increasing with temperature. So we are applying temperatures from 200 to 500 Kelvin. And you can see here the rate for reaction 1 is going up, and similarly R2 is also going up. So that's something important to note, that all rates will rise with temperature. And you can see with the functions here, they both have the same monotonic style of behavior with temperature. So both rates will increase with temperature, but one rate will dominate the other, and then that will influence your net rate of reaction. So depending on which rate goes up more, your net rate will change. So it seems that on balance, you get an increasingly negative net rate of consumption of A. So A is being formed more than it's being consumed. So because formation rises faster with temperature, you will on balance form more of A than the reverse. So anyway, the important thing is all rates will rise with temperature, but it's the competition among those rates that decides on the net result. Okay, and now in terms of the equilibrium relationship, this is what we just established. And now we are interested in relating this to the conversion. So we'd mentioned something called the equilibrium conversion. And so we'd like now to establish what this equilibrium conversion might be. And we can go ahead and just rewrite our concentrations in terms of conversion. So we know that for component A, right, if X is based on A, and remember we have to choose our basis component, so if we define X to be the conversion of component A, then clearly the concentration of A is going to be Ca naught times 1 minus X. So CAE would be the 1 minus XE. So at equilibrium, there exists some equilibrium conversion of A. And so we can replace CAE by CA naught 1 minus XE. And then if we assume that there wasn't any product originally in the mixture, then component B only comes from A being converted to B. So the amount of component B that will occur in the reaction space, that must be the amount that was converted from A. So the amount of A that was converted is, of course, Ca naught Xe. So we can replace this equilibrium concentration of B by this quantity. And so that's the relationship that we have in terms of conversion. And then, of course, you could easily group out Xe here. And you can see it's all linear in Xe, so it's very easy to write here Xe into, you could easily write Xe into minus Ca naught. So that's grouping that part out, and then bring this one across from here. So this will be minus Ca naught over Ke. And then we had left over here a Ca naught, and if we take that across that side, it's Ca naught. And there you can see Ca naughts in all these terms. We can divide everywhere by Ca naught, and so that's going to give us simply this thing. So it's going to be a minus 1, and sorry, I was supposed to write in a minus here. Minus here. Let's just do this on a new line. So we can rewrite this, we can cancel that minus everywhere and divide by Ca naught. So that's a 1, and then this is 1 plus 1 over Ke. And so if you divide through by this and multiply top and bottom by Ke, then you can easily see that you get this expression. So that's nice. We can now find a relationship between Xe and the temperature. Right, remember Ke is quite easy to get, right? We know Ke is simply K1 divided by K2, and both these are well-defined temperature functions. So we simply use the Arrhenius expressions here for each of these, and then we'll get K1 and K2, and those are both varying, and so we can say Ke is a function of temperature. So we can get a set of numbers here, and we can apply those numbers in here, and that will give us a set of numbers for Xe. So this is telling us clearly that Xe can be estimated as a function of temperature. So that's useful. We can find our conversion, our equilibrium conversion, as a function of temperature. And in fact, I'm just going to skip ahead here to an example. So here we are given the equilibrium constants in terms of the Arrhenius expressions. So we've got K1 and K2, and then we go ahead and do that exercise. You generate a series of constants for different temperatures, and you can see here we've generated temperatures in this range. And so we can then find K1 and K2, and then we take Ke equals K1 over K2, and then we just use that expression for X, and then that gives us this nice line here. So don't worry about these other contours as yet. We'll see how to get those just now, but we've got the conversion line here. So if we were to plot conversion versus temperature, we can get that line, that so-called equilibrium line. Okay, so that's one useful relationship that we'll come back to. And then we can also think about, is there another way to establish this equilibrium constant? So we know that if we have the kinetics, if we have K1 and K2 as functions of temperature, then we can get Ke as a function of temperature. But sometimes we don't have K1 and K2. So sometimes we aren't given the full description of the kinetics, and yet we feel that the equilibrium constant is important. So we can, from our thermodynamics relationships, use the Van-'t-Hoff equation. So please go back to your thermodynamics notes and look up the Van-'t-Hoff equation, and you'll see that we can estimate the kinetic rate, the equilibrium constant, and that it occurs as a derivative, and it depends on the heat of reaction. So in your Van-'t-Hoff expression, you've got the heat of reaction as a function of temperature divided by RT squared, and then that is equal to the derivative of ln Ke. So you can use this nice relationship to estimate the temperature dependence of Ke, and especially if you don't have K1 or K2, then this is a useful thing to have. Then in terms of using it and extracting numbers from it, we can think about expanding this further. So we had said before that the heat of reaction may be expanded into the standard heat of reaction, so the heat of reaction at some known reference value, and then the departure from that reference value. So if this is if this is available at T ref at some reference temperature, and we actually want to operate at temperature T, then we have to add in this little bit here to account for that. And so that's how we can expand on that term. And then if we just integrate both sides with respect to temperature, then you can see you're going to be integrating from T1 to T. So that's simply the function that was in the derivative. If you integrate it, it's simply the difference in that function there. And then you integrate here, and noting that you've got a T and a T squared there. So if you integrate the right-hand side, you get that kind of expression. So that's how you can use the Van-'t-Hoff equation to estimate the the equilibrium constant. And then here, this is what we already said. If you have K1 and K2 as Arrhenius expressions or expressions referred to some reference value, then you can also just take their ratio. And so that's all shown here. And if we use this expansion and we follow the maths, you'll see here that we get exp of E1 minus E2. So the difference between the activation energies turns out to be the activation energy of the equilibrium constant. Right, so if you look at this and say, hey, my equilibrium constant has an expression that looks similar to an Arrhenius expression. So in your Arrhenius expression, you have a constant times e to the power, and then there's e over r t, and so the equivalent pre-exponential factor, if you like, k1 naught over k2 naught. So the pre-exponential factor ratios of the competing reactions, and then the difference in their activation energies is the activation energy of the equilibrium constant itself. So you have all these nice relationships to take advantage of if it so happens that you don't have enough about any one of those rate constants. Okay, and you can look at other simplifications. So if your delta Cp is small enough, then you can neglect this term and this term, and then you'll be able to see quite easily that the heat of reaction is actually your difference in activation energies. And that's a tremendously useful relationship, right? Because we have already talked about how to estimate the heat of reaction. So we know we can get a number for this, but it's sometimes difficult to get activation energies for individual reactions. But now it turns out that the difference between those two activation energies is actually the heat of reaction. So that's an extremely useful relationship. So you see, don't look at this course as being completely in a silo away from your other courses. The thermodynamics relationships do yield some very useful connections. So anyway, however you choose to do it, you get the equilibrium constant as a function of temperature, and then you can exploit that to establish how your conversion behaves at equilibrium. Okay, so further, there is this this example. So you are given the Arrhenius expressions, and you are asked here, what's the heat of reaction? And you see then that sometimes you can estimate the heat of reaction from the kinetics, right? So far I've been talking about, well, maybe the kinetics are not available. But on the other hand, if your kinetics are available, then you could say, well, E1 minus E2 is heat of reaction. So I can just look up my activation energies, and the difference between those two is the heat of reaction. So that's answers that one. And then, yeah, how does the equilibrium curve look? So that's shown here. It says also switch the rate constants for the two reactions. So make this one K2 and make that one K1. So we know when you don't switch it, it looks like this. That's your equilibrium curve. When you do switch it, you see it slopes the other way. And we'll talk about just now what that means and how that translates to physically what we're doing. Now, well, in fact, some comments are made here, yeah, about it being. We know if your heat of reaction is positive, then that means your reaction is consuming heat, right? Heat of reaction being positive, that means your products are at a higher energetic state than your reactants. That means that your products have taken in for that reaction to happen. You've put energy into the reaction. So your reaction has consumed energy. So this term heat is a bit misleading. It means it's your reaction has consumed energy. That means your temperature tends to go down. So if heat of reaction is positive, your temperature goes down. If heat of reaction is negative, then your reactants are at or your products are at a lower energy state. So as the reaction proceeds, the reaction gives off energy. So your chemical energy is converted to thermal energy. So you experience that as a temperature rise in your exothermic reactions. So that's an important thing to note. And if you think about it, it means that let's take the first case, endothermic reactions. That means if you increase the temperature, you will be forcing the forward reaction to be retarded, right? So as you increase temperature, your reaction will shift more towards the reactant side. So that explains the slope of the curve shown here. Right? We'll talk a bit more about that later. Okay, so now we are asked, what if we are not just interested in this equilibrium state? And if you think of it, equilibrium is not the most interesting curve to us. We actually don't want to be at equilibrium, right? We said equilibrium is where the reaction rate is zero, right? So at all points along this curve, the net rate of consumption of component A is zero. And that's the opposite of what we want to do as chemical engineers trying to build a reactor. We don't want to be at equilibrium. We want a nice high reaction rate. We want Ra to be as large a number as possible. We definitely don't want it to be a zero. So we can draw this line, no problem, but we want other lines. We want to know how to draw this line where Ra is not equal to zero. So to do that, it's a simple extension from what we've already been doing. So we can say the net rate of reaction of component A, R1 minus R2 KCA minus K1CA minus K2CB. And then we can just go ahead and replace CA by CA naught 1 minus X. And so this X is not an equilibrium X anymore. This is the conversion of component A. And CB, which is CA naught X. So that's there. And we can then group this with respect to X. So grouping X out here, so that's minus K1 CA naught and then minus K2 CA naught, and we've just grouped out the minus. So you group out the X part, and then the leftover part is just this K1 CA naught, and all of this is equal to RA. So you can say X equals RA minus K1 CA naught divided by minus the stuff in brackets here. And that's exactly what we write here. So that's how we can find conversions dependent on a specific rate. Or another way to say this is, if we wanted to know how that conversion curve looked for a reaction rate, a net reaction rate that was not zero, then we would just go ahead and use this expression. So that's how we can generate an iso rate line. We can find the relationship between X and T temperature through this expression if we fix the value of RA. And here, just a note that your CA naught, if you just divide top and bottom by CA naught, you get a slightly better expression. And then the special case, RA equals 0. So if RA is 0, then that knocks that out, leaving you with K1 over K1 plus K2, and you can divide top and bottom by K2 and get KE over KE plus 1. So we've seen this part already. So we've so far been talking about a special case RA equals 0, but there's, well, I don't want to say there's nothing special about that, but it's actually a case to avoid. We'd rather explore more attractive RA possibilities. And I've written some Python code to help draw this, just to show how easy it is to do. So here you can see I'm just bringing in the NumPy and the plotting library. So you don't really need any fancy libraries, just plain old NumPy will do. And then I like to create a separate function which returns all my constants to me. And you can see here there's nothing unusual inside this function. So this function generate constants, and here I'm specifying the universal gas constant, and here I'm just putting in my expressions for the Arrhenius. So the pre-exponential factor and the activation energy, and divided by RT. Noting BODMAS rule that we're using in Python here, and noting that the exponential function is not available by default. So the only reason we brought NumPy in was to access the exponential function. So that's the calculation for K1 and for K2, and then obviously your equilibrium constant K1 over K2, and then we just return it. So in Python you are allowed to just send out lists of things like this, and you can receive the list like this as well. So we create a set of temperatures here between 300 and 800 Kelvin, and here I'm using 1,000 points. So you are familiar with the Lin space function, so I'm just generating a vector of values for temperature, and I'm sticking that vector in here in gen k, and then in Python it will recognize this as a vector and treat it properly and return for us all the constants that we want. Right, so that generates the kinetic constants as a function of temperature. And then what we want to do in our equation, so we've generated all these numbers. We also have to consider a set of reaction rate values. And so here I'm using a log-spaced set of values. So -8, that means 10 to the power -8, and this is 10 to the power -3 using 6 points. And then I just go ahead and evaluate that equation. So it's the same equation, I'm just using this form of the equation. RA over CA naught, so that's the RA I'm using there. So we have to run this equation for each choice in RA. So just be careful here, there are two different dimensions. You've got temperature dimension and you've got reaction rate dimension. So if we loop over the reaction rate dimension on each iteration of this for loop, we are looking at a different reaction rate, and so we generate this set of values which are varying in temperature, and then we redo that. We generate a whole set of values for temperature for each choice of the reaction rate. And then you'll see here I'm just going ahead and plotting the results of that. I am restricting our conversion to between 0 and 0.5, and here's the result. And if you look here, you see the high rates are down here, right? So at 10 to the -3, that's right down there. Then you go 10 to the -4, that's that line. 10 to the -5 is the red line. 10 to the -6, and so on. So as you go to smaller and smaller values, you can see it's converging to this curve that's out there. And in fact, we can increase that, maybe go 10 to the minus 10. And so we'll use 8 values, rerun that. And now you can see they've converged quite closely. Eventually, you can't see it because it's lying so close together. So these are extremely low reaction rates. So anyway, this is a so-called iso rate line curve. You've got curves which have the same reaction rate on them, right? So you can pick a line here and say I'm interested in 10 to the minus 6. So then you can identify on this plane the relationship between x and t that gives you this specific reaction rate. So once more, we know that reaction rate is a strong function of temperature, but reaction rate is also a function of concentration. Now, conversion conversion can be used to, we can use conversion as a proxy for concentration. So we can use conversion to relate to the concentration currently in the reactor. So if you like, this is an indicator of concentration and this is an indicator of temperature. So on this plane, there exist multiple reaction rates. So for each combination of conversion and temperature, there exists a specific reaction rate. And I haven't drawn, obviously I'm not trying to draw on every point in this plane. So if I were to pick a conversion 0.1 and a temperature 500, then that defines a point here. And at this point, there exists some reaction rate. Or saying it differently, if you had a reactor where 0.1 of the reactant had reacted and that temperature in the reactor was 500 Kelvin, then we know in the reactor there'll be some reaction rate that corresponds to those choices. And so there's some number here for reaction rate. And that number must be between these two values. So those two, so the reaction rate there is somewhere between 10 to the minus 4 and 10 to the minus 5. Right, so try to get comfortable with these iso rate plots. You must think of this really as a field of reaction rate values. And so we are going to use this plot for graphical construction. So it is important to be able to think your way through this plot. We are going to talk about moving around on this plot, and so we need to understand what drawing a line on this plot actually implies. So that's the iso rate plot. It might also occur to you, well, what about this big empty space here? Is it that nothing is going on there? Well, it's just because we chose to look at positive rates. In other words, rates where component A is being consumed. If we just set RA to a minus value, in other words, where A is being consumed, and we run that, then you can see you've got lines up here instead. So there's no prescription that nothing is happening out here. It's just that this region is less interesting to us. We don't want to be forming a reactant. We want product forming. So we don't want to be up here. It doesn't mean nothing is happening up here. We might accidentally stray up here, but that wouldn't be a good thing, right? So we don't really draw over there, but that does exist. Okay, so those are iso rate lines. And now we want to talk about negotiating our way around those iso rate lines and on that iso rate plot. And from our energy balance exercise, we had established this relationship. So we said if we have a reactor and we allow the species to react to some extent, the temperature will change and there will exist a relationship between the conversion achieved and the temperature in the reactor. So do go back and really understand what this equation means. So this equation is telling us that as the species react, then necessarily the temperature is going to change. Noting that this is the adiabatic form of the equation. So in an adiabat, you are not adding or removing heat from the system. So if you are not controlling the temperature in any way, if you allow the reaction to proceed, the temperature will change. So as the and remember, if our rate is positive and the system is moving, so the system tends to move in some direction, and so here the conversion will tend to rise. So for example, imagine this is in a batch reactor. So you've got a batch reactor, you've fed that reactor with components, with reactants, and so the reactants are reacting away, and so your conversion is rising. So as your conversion is rising, your temperature is either going to rise or fall. So if it's an exothermic reaction, delta HR will be negative, so this will overall be positive. So as conversion goes up, temperature goes up. So you can see here an exothermic reaction agrees with what we can see. So as conversion goes up, temperature goes up in the case of exothermic. For endothermic, delta HR is positive, and so this is on balance negative. So as conversion rises, temperature drops. So that's what's happening in the reactor. And we haven't drawn that as yet on this plane, right? We'll draw that line just now. But this plane is more like a plane of possibilities. So this plane is kind of hands-off. It's just saying, I don't care what you are doing, where you are reacting it. I'm just going to tell you, if you go and convert your reactant by this amount, and if you are doing it at that temperature, then that is the reaction rate you have currently. If you go and do it at that point, then that's the reaction rate, and so on. So this is just telling us how the reaction rate itself is varying. It's not telling us anything about how we are progressing the reaction in our reactor. So let's go and draw that line on that plane now, and we can start thinking about what's happening there. Here, in this example, we are again given the kinetics. We are told we have pure A, so that means there's none of component B initially. We start out at 250 Kelvin, and we are leaving at 320 Kelvin. And it doesn't say, it says what's the conversion according to the energy balance. So to find this out, we look at this expression. You can see we need the heat capacities here. It's pure A, so theta B is 0 and theta A is always 1, if A is the reference component. And then that means we just need CPA here, and so A and B are given, but you actually only need component A. So we've got heat of reaction, and then the heat of reaction, like we said, is the difference between E1 and E2, and then it's T minus T inlet, which is 250 Kelvin. So let's write out the equation of this line. So I'm just going to copy this equation here, and I'm going to say x equals, and in fact let's do it carefully. So let's say it's going to be theta A CPA plus, and that's theta B CPB, and divided by the heat of reaction minus delta H super R, and then times T minus T in, so T minus T sub in, and let's put the numbers in. So theta A we know is a 1, and then CPA is given to us as 100. So 100. And then theta B, we said it's pure A, so theta B is 0. And CPB is 400. And then the heat of reaction, we said, is E1 minus E2, activation energy 1 minus activation energy 2. So it's 30,000 minus 53,520, and T in is 250 Kelvin. And that's it. That's enough for us to go and draw that line. And so it may have looked pretty scary in terms of all the subscripts and the Greek symbols and so on, but when you interpret these, you see it's really quite simple. So this turns out to be just 100 over a number which you can see is positive, right? 30,000 minus 53,000, that's negative, and then minus of that is a positive number. So it's 100 over some positive number times t. So x is some positive constant times t, and then you can see x equals 0 at 250 Kelvin. So let's go ahead and plot that line. So 250 Kelvin is there, and then if you use that ratio, right, that's basically your gradient with respect to temperature there. So if you just plot that gradient, you can see this line is pointing in this direction. So what that tells us is that as the reaction proceeds, as x rises, your reaction is moving up in this direction, and you see it's pointing straight at the equilibrium line, right? And that's always the case with nature. Nature is running downhill all the time. It's always trying to get to a lower energy state. So, and I wish I drew arrows on here, but if you start, maybe let's think about some of the other numbers here. So we know we enter at 250 Kelvin, and we know the conversion is 0 there. So conversion being 0 means your concentration of component A is fairly high. And if you look here at the numbers, at the isorate lines, right, 10 to the minus 8, 10 to the minus 7. So the reaction rate at this point is somewhere between these two values. So maybe it's something like 2 times 10 to the minus 7. And so whatever the exact value is, and I don't really care what the exact number is right now, but whatever the number is, it's a positive. So it's a positive consumption of component A. So when you know that the reaction is that there is a consumption of component A, then you know that there's a tendency for the conversion to rise, right? Your component A is being on balance consumed, so the reverse reaction is not high enough. So your forward reaction is faster. So your conversion is tending to rise. And it's not always the case. Conversion can also go down. So if you are in this region here, where your conversion of B back to A is higher than A to B, then if you are here, your conversion actually goes down. But anyway, we are here, conversion is going up. And then it's an exothermic reaction, which means on balance, your thermal energy is rising. So you are getting heating, your reaction space is going up in temperature. So as your conversion is going up, your temperature is also going up, and that means you are moving along this line. Now that's all well and good. We can say, yes, let it keep going. So it rises, but you see, as you get in here, your reaction rate is dropping, and in fact all the way, well, most of the way here it was rising here, then it started dropping, so it started getting closer to 10 to the minus 7. So here we were 10 to the minus 8, we were some number less than 10 to the minus 7, and then the rate went up, and then it probably still went up, and then it started getting back close to 10 to the minus 7. Then you go past this point, you see you are now getting closer to 10 to the minus 8, and then in here 10 to the minus 9, 10 to the minus 10, and then you're getting closer and closer to the 0 point here. So your rate is really going down as you get closer and closer to equilibrium. So it's nice to go and draw this line, but you have to realize that as you do this, it might be that there's tremendous effort involved in that reactor. That let's talk about it like a batch case. So initially we might have had a nice high rate, and the conversion stepped up here within 30 minutes or so. But then as time went on and the rate went down, to get even a small change in conversion out here, it took a very long time. So as you get closer and closer here, it actually takes more and more time to get the smallest improvement in conversion. And eventually you get no improvement in conversion. So there's an equilibrium value here, which you can actually never reach. And so you can't go past that point. So the equilibrium line actually establishes for us a kind of constraint. So we can build the reactor, but if we build over here, we will need a long time to accomplish this conversion. The rate is too low here. Or if it's a CSTR or something like that, you'll need a massive CSTR to work at a point close by here. And an important thing to notice, this is for our designs, is that for very small changes here, you need massively different size reactors here. So down here, let's say it's a 50 cubic meter reactor. Then suddenly you need a 100 cubic meter reactor, a little more, and you need 1,000 cubic meter reactor. You need kilometers tall towers. So over here, your volumes, your reaction volumes or your reaction times are crazy numbers. So this equilibrium line represents a region that we want to avoid as far as possible. And we in a sense are constantly being driven to it by nature. Nature wants to run downhill and reach its equilibrium state. And we as engineers have to kind of corral nature and keep nature away from equilibrium so that we can still accomplish something, so that we can still convert to a product. And you see here, it's kind of a disappointing place, right? If this was our reactor, you can see we can't do very much here. We can only, for these unfortunate kinetics, we can only get about a 30% conversion here. And that's where we've applied refrigeration, right? I normally think of 300 Kelvin as a kind of magic number. So if you can operate at 300 Kelvin, that means under ambient conditions, which is about 300 Kelvin, you are talking about ambient conditions. And if you need to cool, right, cooling is a lot more expensive than heating in engineering. So cooling, that means you need refrigeration plants just to get down here and get there. If you are operating under more reasonable conditions, let's say 300 Kelvin, you are stuck to an even lower conversion. So as you raise the temperature here, yes, you increase both reaction rates, but it turns out that your reverse reaction rate is actually increasing faster, to the extent that you don't get much conversion. Your conversion is too low in this case. So this is an important consideration in equilibrium reactions, and this equilibrium line is something that helps us understand what kind of limitation we can experience and how that's going to influence our design. So coming back here, right? So that is what we have in the exothermic reaction case. And if you do the same exercise now for the endothermic case, you'll find that the line slopes in the opposite direction. So let's say our starting temperature was 450 Kelvin. And if you go back to the equation, this equation, if it's endothermic, then delta HR is positive, and so this is on balance negative. And so you can see here your slope is negative now, and your equilibrium line slopes this way. And so again, you can see nature is starting out somewhere not at equilibrium, but it's pointing itself straight at equilibrium. It's trying to get back to equilibrium. And so your rates are dropping. So you're getting closer and closer to equilibrium. but as engineers, it's not helping us. It's getting us to a rest state. We don't want the system to be at rest. We want it to be doing active things and producing products for us. So we can see the lines always go towards equilibrium, but we can think now, is there something we can do about this? What could we do to improve the situation? Right, we'd like to get to a nice high conversion. We want to get to maybe 80% conversion up here. Is there a way to do that? Can we think about a reactor design that can help us negotiate this plane? And you can think about back when we talked about the Levenspiel plots. Our solution to improving our design was to break that reactor down into a small set of reactors, and so we could really reduce the volume of the reactor. Is there some similar strategy we can use to get to higher conversions? So think about that. Maybe pause the video and give yourself a chance to answer that question. Right, so hopefully you've thought about that, and there are a number of things we can consider doing. Number one, we could design our reactor to go this far, and we say that's fine, but I know I'm getting to very low rates here, so I want to do something at this stage. And a simple thing we could do to travel around this plane is simply cool down the reactor. So if we, at this stage, when we reach this point, if we simply add, maybe in our cooling jacket, we pulse a lot of cold medium, or well, there are many ways to cool down a reactor. So if you cool down the reactor without adding any materials, so you are not adding product or reactant, then your conversion won't change, right? You've still got the same amount of product here and the same ratio of product to reactant. So X is not changing, and you are just cooling down. So that means your temperature will drop. So that means you can talk about moving horizontally here. And let's say you cool it down all the way to 250 Kelvin. Then you see you've forced nature back to a state where the rate is still positive. And then you let nature do its thing, so nature will start rising again and going up to this point. And then again, as you get closer to the low rates, you can say, well, let's just use some cooling again, and you pull it back here, and so on. You can do that as many times as you like, and so you can sort of squirm your way up the ISO rate lines. Noting that the rates up here are lower, so you will need, on average, bigger sized reactors here, but you can do that. It depends on the economics, right? If the increased costs of making bigger reactors is attractive when compared with the increased costs of separation with such low conversions, then you do that. So to say that again, if you accept a low conversion like this, that means you will have a low concentration of product. That means you have to do a lot of separation. You need many distillation columns to separate your reactant from product, so you can recycle your reactant. So there's a certain cost to that separation, and then you have to weigh that cost against the cost of building more reactors here. So this is where we start to touch on design. This is where you have to think about the roles of reaction and separation, and it's the two working together that decides on a good reactor design. But anyway, from the perspective of the reactor, this is what you can do, right? You can negotiate your way up the plane like this, and physically, this is what we would do. So you would have your CSTR, and then coming out of the CSTR, you would put in a cooler, a heat exchanger that cools down the content, and then once it's cooled, it goes into the next reactor. So you can actually identify each of these stages as lines here. So the first reactor does this. The reactor itself is actually operating on this point. So that's the first reactor. And there again, you can estimate the volume. So if you know you want to go to that point, then you just you read off the rate there, and this is easy. It's 10 to the minus 7. So you use your design equation. So V equals reaction rate times molar flow, and so on. So you can, if you've chosen a point here, then that specifies a volume. So if you've made the reactor that volume, then it will exit at that point. And then you can identify this line as your heat exchanger, and you know now that the duty on this heat exchanger is it needs to go from 325 Kelvin down to 250 Kelvin. So that specifies the temperature change across here. And we also know the heat capacity of the species passing through, so we can estimate the heat load there. So you need to design a heat exchanger that accomplishes that temperature change. And then that's the temperature going into the next one, and then that whole reactor is operating there. So you choose where to stop here. That defines your reaction rate, and so you can estimate the volume of that reactor. Right, so that's the strategy there. Okay, so here's another example. Consider the same conversion, the same species, and this time we want to use 3 CSTRs, and we want to operate them adiabatically but with interstage cooling. So the reactors themselves don't have jackets or heating coils or anything like that. But between the reactors, we have heat exchangers. So that's what this one is doing. Your inlet temperature to the first one is 300 Kelvin, and you are told about the interstage temperatures also. And we are given the heat capacities, and we can see we likely won't need CPB. And so what's the exit conversion from the cascade? And here's the solution. So because we are simply given the temperatures, and because we can work out the slope of this line, right? Remember from the energy balance, we could get the slope of this line. So you know the starting temperature and the slope and the stopping temperature. So we are told it's the exit temperature from the first reactor is 440. So the first reactor is 440. So you just draw for 440 along that line. So that's where you stop. And then we are cooling back to the original temperature. And then the next one is at 400, and then the last one is at 370. So you just do that, and then you read off here, yes, my conversion there is 0.84, it looks like. Okay, so that's how we can design these types of reactors. That's how we can negotiate this plane. Now, in terms of optimizing that temperature profile, so you see the problem here has kind of arbitrarily chosen 370, right? We'd like to be cleverer about this. Instead of just saying, oh, 370, 470, 400, and so on, we want to pick a good value here. And of course, we would like to go as far as possible along this line, but we also know the rate is dropping. And so we need to optimize this choice. We need a better criterion for where to stop along this line. And the first thing we could do is think about where the maximum rates lie. Well, you might say, well, clearly the maximum rate is here. So that's true. But when we move around here, where are the best rates to operate on? And if we think about it, that depends on the type of reactor we have. So if we are operating with a reactor that's moving along this line, we can think about what's happening over the lifespan of that reactor. Let's imagine it's a batch reactor. So when that batch reactor starts off, it's increasing in conversion, and then the rate, you can see the rate is changing here. So the rate on this side is 10 to the minus 6, the rate here is 10 to the minus 5. So we are on balance moving closer to 10 to the minus 5. So the rate is increasing here, it's increasing, we are getting closer and closer to 10 to the minus 5. So it's pretty high here. And then we are starting to go past it, we are going back to the 10 to the minus 6 point. So you can see here, we are at a lower rate than we were here. So the closeness of our line to the higher rate is a good estimate of where the maximum rate is. And in fact, we can do that explicitly then. We can say, let's just shift this whole line to be tangent to this ISO rate line. So based on this idea of closeness between this line and this curve, you can see if we shift this line until it is a tangent to this curve, then you've identified a closeness point. And so even though our actual reactor might not be operating on that line, we could simply shift this line around, right? We know all our reactors are going to have the same slope here. So we could shift that line around. We could just draw a hypothetical line with that slope and shift that line here and say, okay, that's a maximum rate region. Then we can shift that line here. We can say that's a maximal region. Shift it here, maybe the point is here and the point is here, and so on. So we've identified a series of points where the rate is nice and high. And so we can draw a line here and say along these lines, this is the best region to be in. So that would then define the point where we should operate that reactor. So for example, if we had connected that line in that way, then we would say, okay, that locus of points line is somewhere here. And so that's actually the best choice for the CSTR. That's where we would get the maximum rate. So we can operate on the so-called maximum rate line, and then that would give us the minimum volume in that CSTR. So that would be a clever way to negotiate this plane of possibilities, this plane of all possible reaction rates. Right? So that's the first comment on optimality and optimization. And then we could also think about trying to stay close to that line overall. So if we've drawn, excuse me, if we've drawn this maximum rate line, and in fact, let's try and draw it somewhere. So we've identified maybe a point here. Let's use a better color. So maybe we've identified a point here, and then from the slope it looks like there'll be another one there, and then maybe another one there, one there. So you can draw a series, or you can draw a line. Oops. Let's see, drawing with the mouse is not so easy. You can do this much better. So let's say we've identified the so-called maximum rate line. So we can say, well, then this reactor should stop here. And then, in fact, we can cool as much as possible. And then we react up to that maximum rate line again, cool as much as possible, react back up there. And so we know then that these points are in the best possible region. We've got the best possible reaction rate here, hence we've got the smallest possible reactors. That doesn't mean to say they will be feasible reactors. Even the best reactor might be too big. So as you get to regions out here, you might find the reaction rate is just too low to get a reasonable size reactor. But still, this is the best that you can do. Right, so once more, if you look along this line, then you are looking at different RA values. And then you can see this rate is lower than this rate. So the closer you are to this line, the more optimal you are. And so if we take advantage of that and say, well, I can just take a point here, and or I can take a line with the same gradient, find the tangency point, and then I do that for each ISO rate line. So you find all the tangency points and then connect them with a continuous line. Then that tells you where to operate the optimal reactor. Now, that is the best way to do it for minimizing your reactor volume, but that might not be the only criterion. So you could say, well, you are still requiring me to stop short of my full potential. You could say, by just going further along this line, I might get to my desired conversion. So let's say our desired conversion was 0.35. So even though the intersection here is just short of 0.35, we would then say, well, with just a bit further, with just accepting a slightly suboptimal solution, we can accomplish our goal, we can meet our specification. So we would rather just operate there, and then we don't have to use a whole other reactor. So there are many other costs every time you add another reactor. So you need to create a whole other maintenance plan, and you have to create a whole control system. And so there are many other capital costs each time you add another unit. So sometimes you'd rather just make the unit a bit bigger. And there is a criterion for that other for that other strategy. So typically we want to stay 10 degrees away from equilibrium. So if you look along this line is pointing at a specific equilibrium here. And so if we say, I want to stay 10 degrees away from equilibrium, you can figure out where equilibrium is. In this case, it's at about 450 degrees. So you want to look for 440 and say that's my equilibrium, that's the margin I want to stay away from equilibrium. Similarly here, if you look along this line, you can see equilibrium is at this point. So if you say I want to stay 10 degrees short of that, maybe it's there. And similarly here, here's equilibrium and here's the point. So the other criterion is if you want to have fewer reactors, then you can draw a different line, a 10 degrees short of equilibrium line. So this is a typical engineering style of a thing. We just use a rule of thumb. We say 10 degrees short of the worst possible case. And so we can instead, if we want to go for fewer reactors, knowing they are suboptimal, you can use the 10 degrees to equilibrium line. So we'll look in the coming sessions at using this idea, using this concept of moving along the operating line and negotiating our way. We'll look at that in the context of the CSTR, the PFR, and the batch reactor. I think there are one or two more comments to make though. So this was all describing the situation if we had the adiabatic case. Remember this straight line we got is for the adiabat. That means we are not adding heat or removing heat from the system. And we need to correct this line if we are adding heat to the reactor. So if we go back, right, this was the adiabat that we said we were drawing. That's that line. And then if you go back and say, well, actually I am adding or removing heat, so I need to retain my Q dot term, then you just you go ahead and expand out for Q dot. So whatever form you are using for Q dot, so you usually have some dependence on temperature in there. So you substitute your function for Q dot there, and then you resolve that equation. Well, I guess that's what's already done here. So it shows you how the equation looks when you have Q dot. In this case, it looks like it's just an offset, and this equation is still linear. But in some cases, Q dot is actually a function of temperature. And then you have a slightly more complicated situation. If it's still linear in temperature T3, then the whole thing is still linear, but this might not be so nice and linear. So but it doesn't really matter. You just substitute the function for temperature in here, and then that may change your curve. So instead of a nice flat line, you might get a curving line or something like that. So that's all you need to do if it's not the adiabatic situation. So you see, even in the case of complex kinetics, there are interesting things to think about, and we can negotiate our way around this isorate plane and we can develop good designs even though it's looking more complicated.